Welcome back, everybody. It's the second lesson in Unit 6 Meteorology, and today we're going to be discussing moisture in our atmosphere. And of course, it's a very crucial substance in our atmosphere. It has a lot to do with weather. So first of all, how does that moisture get up into the air? Well, we know it happens from a process called evaporation, and to a lesser extent, transpiration, which we'll also talk about. Transpiration is from plants. But for evaporation to occur, water must absorb energy, and that energy comes from our sun. And the energy that it needs to absorb in your reference tables is represented by 2,260 joules, which is a measure of heat energy, per gram. So for every gram of water vapor to go up into the atmosphere, the water, for instance, from a lake or an ocean, must absorb 2,260 joules of that energy. And it's kind of potential energy, stored energy. All right, some factors affecting how fast things evaporate. Well, obviously, if it gets warmer, if you increase the surface area by spreading out the water, increase the wind speed, or decrease the amount of water vapor already in the air, that means dry air, these four things are going to increase how fast water evaporates into the air. The middle two you can kind of think of as those little hand warmers in the bathroom that blow hot air out. You rub your hands together to increase the surface area, spread the water out, and you also have that fan blowing high-speed air, and that definitely evaporates that water much faster. There's a lot of water vapor in the atmosphere right now. This number here I pulled off of, I think it was the NOAA website. 3,100 cubic miles seems like a lot, but that's what they said. How many miles of water vapor, cubic miles of water vapor in the troposphere right now? Amazing amount of water. So what's this called? Well, we call it humidity, the amount of water vapor in the air. And we know that as air temperature increases, it can contain more water in the form of water vapor. You can see that by the upward curves on the graph to the right, which we're not going to get too much into now because they talk about some things I haven't taught you yet. All right, now what we're going to be using more of in this course is not humidity, but relative humidity. And you've probably heard this many times on the 6 o'clock meteorology forecasts. Relative humidity, the amount of water vapor in the air compared to the maximum amount possible, and here's the key part, at a given temperature. Relative humidity is temperature dependent. Now, if you look in this diagram here, you'll see three sets of situations, 10 degrees, 20 degrees, and 30 degrees Celsius. And in the 10 degrees Celsius situation, you'll see water vapor at 100% relative humidity. Now, in the second temperature, 20 Celsius, you notice that yellow area. That yellow area represents warmer air and its ability to have more water vapor contained in it at that temperature. So you can see at 20 degrees Celsius, more water vapor can exist in the air. But if it doesn't exist in the air any more than the first picture, that means our relative humidity is lower, 52%. So you can see it's gone down. Now, if you heat up the air even more to 30 degrees Celsius, the yellow area representing how much water vapor could be contained in that warmer, more energetic air is even greater. But if you don't allow more water vapor to evaporate into the air, the relative humidity is even lower. So what this is saying is that air warms up and you don't have any more water in the air, doesn't evaporate into it, your air actually gets drier or lower relative humidity. And vice versa, if it cools down, it gets higher relative humidity. Now, the temperature at which the air becomes saturated, we call it the dew point, or the dew point temperature. And that's when the relative humidity is at 100%. Which temperature to the left is the dew point temperature? You can see of those three, which one's at 100% relative humidity, and that is the 10 degrees sample. Without changing that 30-degree temperature over on the right-hand side of this picture, is there anything else we could do to change that 28% relative humidity to 100%? So if we don't change the temperature, if we don't lower it to 10 degrees, is there any way to get that 28 up to 100? Well, if you think for a moment, we could just somehow make that blue circle as big as the yellow. And to do that, we'd have to add more water vapor to the air. So that happens in real life too, because there's, it's an open system. There's water in lakes, in oceans. After it rains, there's plenty of water in the ground. Note, dew point temperature is also called the dew point because dew or frost forms on exposed surfaces when the outside temperature falls to the dew point. Now you've had this happen, in gym class. Morning gym classes are notorious in the fall for coming in, you got grass clippings stuck to your sneakers, and your sneakers are all wet because overnight the air temperature cooled down cool enough to make that water vapor turn back into liquid water. You can see it on the blades of grass there, on the window, and if it's later in the fall, you even get some frost on the windows. Make sure to remember the following two things that can raise the relative humidity to 100%. So basically, how can you get that 28% to 100? The first, drop that temperature down from 30 to 10 in this case. That's going to raise your relative humidity. And the second is to get that blue circle the size of the yellow. That means add more water vapor to the air. So those two things happen in nature, and they can make the air become more humid. How do we measure relative humidity? We're going to be doing this in lab class. You're going to go outside. You're going to do it in the classroom. We use an instrument called the sling psychrometer, and it's simply two thermometers attached to a shaft which can sling around really fast. And you're going to sling this thing around for about a minute or so. And there's a wet bulb thermometer and a dry bulb thermometer. The only difference is the wet bulb thermometer has a wet cloth, usually like a shoelace, soaked in regular water, and you sling that thing around, and the dry one simply just sits there and measures the air temperature. But that wet bulb thermometer starts to evaporate. And that evaporation is a cooling process. Just think when you come out of a lake swimming in the summertime and the wind's blowing, you get cold. That cooling, turns out, cools down more when the air is dry. So the drier the air, the more it evaporates, and air that's drier or lower relative humidity has a large temperature difference between those two thermometers. Now, one thing you should realize is the wet bulb can never be warmer than the dry bulb. I've had this happen in lab class. Students come to me and say, hey, this number's bigger than that. My reference tables won't work. And turns out that they used hot water in the sink instead of just regular water. So make sure you use just the cold side of the sink when you're doing this lab. What's true of the relative humidity even after slinging if the two thermometers are equal in temperature? Now, if I send someone outside to sling the sling psychrometer and it's sprinkling out or raining outside, or if it's foggy outside, they come back in and they have essentially the same readings on the wet and dry bulb. That's because that wet bulb thermometer couldn't evaporate any water from it because the air was already saturated, so it couldn't move its water out to the air. All right, finding dew point temperature. So we're going to get out your reference tables now. Here's a quick example. The dry bulb temperature is 16, the wet bulb's 11. The dew point temperature, and if we look on this chart, we go down to 16. This is the dry bulb temperature is here. We go down to 16. I know the answers already showed up there, guys, but just look up on the screen here. And we go over the difference between the dry and wet bulb temperature. We don't go over to 11. We don't go over to this box here. We go over the difference. So 16 minus 11 is 5. So we're going to find out where 5 and 16 meet, and they meet right at 7 degrees. And there's our answer. So it's a pretty simple process. These charts aren't hard to use at all. They're much easier than the old-fashioned charts that we used to use in our science. All right, now there's some other examples here which we're going to stop. We're going to practice. When we get done with this, there's also a set of examples I wanted to do with odd numbers for dry bulb temperatures, because when you have odd numbers, like for instance, let's say I had to go down to a 17, here's a 16, here's an 18, you have to actually find answers for the two numbers that surround where that odd number would be, and then average your answers. That's the only complicated part about this. The rest of it's pretty straightforward. And then there's some other tricky questions that can be asked where you work backwards instead of given dry bulb and wet bulb temperatures, you might be given a dew point or relative humidity, and you have to find either the wet or dry bulb temperature. All right, so hopefully you learned something about moisture in the atmosphere, and see you next time.